Capacitor is a device used to store electrical energy or electrical charge. Usually it consists of two electrical conductors, and the shape of this conductor could be, for example, different. They could be in the spherical shape, cylindrical shape. In our case, for example, I have drawn two parallel plates. Now our two conductors here are these two parallel conducting plates. So that's why the name of this capacitor is called parallel plate capacitor. And there is a distance between these plates, and it could be vacuum. The space between them could be vacuum, but we can also fill it with some insulating materials, which are called dielectrics. And the amount of this capacitor is called capacitance of the capacitor, and it is denoted by the letter C. This capacitance of this capacitor is defined as the maximum charge of the capacitor that could be stored in the capacitor if the voltage between them is U. Okay, so it is maximum amount of charge per unit volt. Okay, so Q is the maximum charge on the capacitor, and U is the voltage applied across its plates. Now, C units of capacitance is just 1 farad, so it's 1 farad, and it's not difficult to see that 1 farad equals 1 coulomb over 1 volt. Capacitance of this capacitor, even though in the formula we have written Q, the charge on the capacitor, and the voltage across its plates, it doesn't depend to these quantities. For example, even though if we can change the voltage across its plates, right? But the charge on the capacitor also changes in this process respectively. So Q over U, this ratio remains constant. And the capacitance of this capacitor depends to the shape of the capacitor. For example, in this case, the size of the plates and the distance between these plates. If the size of the plate is big, then of course the storage of the charge is big. So if you use our intuition, we can immediately say that if the surface area of the plates are big, then of course the capacitance should also be big. If the distance between them is small, then the attraction of the charges on different plates is also strong. So again, it results in increase in capacitance, right? Now we have to derive these things, okay? How now let's derive the expression for capacitance. Okay, now to do so, first of all, we need to find the voltage. Okay, we need to express this voltage in terms of, for example, Q. Okay, to do so, we are going to use the following formula. Voltage is the negative of potential difference, which is given by integral E ds. From okay, now if we sorry, it is dr. Let me write dr, or in our case it is let's say this is x, then we can also write it as x. Okay. If the plate on the left hand side is positively charged and the plate on the right hand side is negatively charged, then the direction of the electric field inside the plates goes to the right in the x direction. So you see the angle between E vector and dx vector is just 0. So we can write it as E multiplied dx multiplied cosine 0, where cosine 0 is just 1, so I'm not going to write it. An electric field strength inside the capacitor is just 0. I mean, it is uniform, it's just constant. So we can take this E out of the integration, and integration of dx gives you just x. And if we integrate it from x1 to x2, we will get x2 minus x1, which is the distance between these two plates. Okay. Now, electric field strength inside the capacitor is given by sigma over epsilon 0. So if we multiply it to D, we will get the voltage. Then capacitance, it's Q over U equals, well, Q divided by sigma D multiplied epsilon 0. If we express this, the charge on the plates in terms of sigma, then we will get sigma multiplied S divided by sigma D multiplied epsilon 0, which is just epsilon 0 S divided by D. You see, the capacitance of the capacitor depends to the surface area of the plates and the distance between them. So it is proportional to the surface area and inversely proportional to the distance between them. And epsilon 0 is just permittivity of the free space. It's just, well, let me write it here. Epsilon 0 is permittivity of the free space, which is 8.85 10 to the minus 12 Newton meter square coulomb square. Let me write it here one more time. So capacitance of the parallel plate capacitor is just epsilon 0 S over D. Okay. Now, well, so to derive this final expression, this formula, we have used that electric field strength between the plates E equals sigma over epsilon 0. But we didn't derive it yet, right? Now, so let me explain where this expression came from. So, if we have one plate, consider that this is positively charged plate, then its electric field strength has the following directions. So, electric field lines are given here. And in the previous lecture, we have showed that the electric field strength of an infinitely large plate has a uniform electric field, and this field is given by, if you use the Gauss law, it was just sigma over 2 epsilon 0. Okay. Now consider we also have another plate which is negatively charged. Then the electric field lines of the second plate is just like this. Well, it's like this. So outside of the plate, now if you look at this outside of the capacitor, the electric field lines of different plates, they are opposite, right? But the magnitude of these fields, they are equal to each other. So they cancel each other because they have different directions, and electric field strength, it's a vector quantity. So outside the capacitor, electric field is 0. Okay, but inside, you see the yellow lines and red lines, they have the same direction. So this means electric field strength inside the capacitor is 2 times bigger than this. And it means that electric field strength inside the capacitor is just this one, right? Which is, okay, let me call it as epsilon 0. Then it's just 2E0. So 2 times bigger than the electric field strength of an infinitely large plate. Okay.